In Module 4, we are going to take a look at circles. So start off in Section 1, we're just going to talk about some basics of circles, some basic properties that they have, and some parts of the circles. So start off with, we're going to define what a circle is. So a circle is the set of points equidistant, which means the same distance, from a point called the center, which is the middle of your circle. All circles are named after the center. So whatever letter you use to indicate what the center point is, that is how we name the circle. So if my center point is A, it's circle A. If it's F, it's circle F, whatever letter that may be. Then we have our radius, which is the distance from the center to any point on the circle. And then we also have our diameter, which is the line segment connecting 2 points on a circle that passes through the center. So key thing here is it does pass through the center. We will talk about in a little bit what it's called when you have a line segment that doesn't pass through the center. We'll talk more about angles later on in Module 4, but for right now I am going to introduce something called a central angle, since we're going to be talking about naming circles and line segments. So a central angle is an angle formed by two radii, which is the plural of radius, that meet at the center of a circle. So for example, I'm going to draw a circle here. I'm just going to go ahead and name it circle A. And I'm going to put some points on my circle. I'll call them B, C, and D. So I'm going to create an angle with my radii BA and CA. And now the angle that it has now formed at A is called my central angle, because it's the angle at the center of the circle. There are technically two central angles formed by just drawing two radii, and that's what we're going to get into next here with our arcs of a circle. So an arc is a section of the circle formed on the outside. So it's going from one point on the outside of the circle to the other. And what we do is we name it using points on the circle. So there are two types of arcs. There's a major arc, which is an arc measuring more than 90 degrees, in which case we use 3 points to name it, so we are indicating that it's a major arc. And then there's a minor arc, which is an arc measuring less than 90 degrees, and we use 2 points to name it. So it is important that the first and third points you use for a major arc are the points of the angle you want to identify. So if I go back to my circle I drew when I was identifying my central angle, my major arc goes from B to C, but I have to include that third letter D. So it's arc B, D, C. And we always just use like an arc over top the letters to let us know we're indicating an arc. I can also write it the other way, C, D, B. These are the exact same thing. The only thing that matters are the starting and ending points. Those indicate what arc you're looking at. For my minor arc, I only have to use 2 letters. So BC is my minor arc. It just goes from B to C. I can also name it as CB. Again, we'll talk more about angles and arcs later on in Module 4, but I do want to introduce them now. Now we're going to talk about chords, specifically chords intersecting inside a circle. So a chord is a line segment connecting 2 points on a circle. So any 2 points on a circle, if I draw a segment between those, it's called a chord. The diameter is a specific chord that passes through the center. So the diameter is technically still a chord. It meets the definition. It is a line segment connecting 2 points. So when we're looking at intersecting chords specifically, it tells me that the product of the segments formed by the two chords in a circle are equal. We are going to also talk about later the relationship between the angles that exist when you have intersecting chords, but for now we're going to focus on the relationship between the line segments. So in order to talk about the formula, I'm going to draw a circle as kind of like an example because it's easier to see it that way. So let's go ahead and name our circle A. I'm going to draw two chords, neither of which are going to be a diameter, just to make it a little bit easier to kind of see what we're talking about. So I'm going to do B, C, and D, E, and I'm going to go ahead and name my intersection point F. So what my formula tells me is that the product of those segments, so BC is made up of BF and FC. So it tells me their product, BF and FC, has to equal the product of my other chord, which is formed by the segments DF and FE. So that's all the formula is. Product of the segments formed by your chords are equal. So let's go ahead and do a couple examples. So in our first example, we're going to have that AE is 10 and EB is 8, and we know that ED is 16. And we want to find the length of CE, which I'm going to label as X. So using my formula, I know that 10 times 8 has to equal 16 times X, since those are the products of my chords. So I get 80 equals 16x, divide by 16, and I get that x is 5. So that tells me that CE is 5. Let's do just another example. So now let's say CE is 6, AE is 9, and EB is 4. We want to find the length of ED, so that one I'll label X. So we have that 6 times X has to equal 9 times 4. So we get 6X equals 36. Divide by 6, and X equals 6, which means ED is 6. So as you can see, I set it up differently in both cases. It doesn't matter which product of segments you put on the left and which ones you put on the right, since they're going to be equal. So it doesn't matter here that I did CE and ED equals AE times EB, which is the opposite of what I did last time. Doesn't matter. Still works out and you get your answer. So the last thing we're going to discuss in section 1 is radians. So this kind of goes back to angles in circles. So we all know that you measure angles in circles using degrees, and that all circles have a measure of 360 degrees inside. But there's another form of measuring angles, and it's called a radian. So what a radian does is it's a unit of measure for a circle based on the radius of a circle. So basically it tells you how many times does the radius fit around the circle. So what we're going to do is talk about how to convert between degrees and radians. So if you have an angle measured in degrees, so you have your angle in degrees, okay, and you want to convert it to radians, you multiply it by pi over 180, and that will give you your radians, which we're going to abbreviate RAD. On the reverse side of things, if you're given a measure in radians and you want to convert it to degrees, so you have your radian, you're going to multiply it by 180 over pi, and that will give you your degrees. So let's go ahead and look at some examples. So we're going to convert between degrees and radians. So I have 25 degrees. So if I want to convert 25 degrees to radians, I'm going to multiply it by pi over 180. And that's going to give me the fraction 25 pi over 180, which I do want to simplify. So what I want to do is I want to simplify the fraction 25 over 180. And 25 and 180 are both divisible by 5. So that's going to give me 5 pi over 36. And then I'm going to put my units for radians, RAD. Your other option here is to go ahead and write it as a decimal, which we're not going to do for a whole lot of the time, mainly because of what we're going to be working on, but sometimes it might be necessary. So 5 pi and then divided by 36 is about 0.436 radians. So not a very large amount of radians. Next, we're going to go from radians to degrees. So I have 1.5 pi radians. So I'm going to write it as 1.5 pi, and then I'm going to do times 180 over pi. So the nice thing is here is if my radians contain pi, the first thing I can actually do is cancel those because I have a pi in the numerator and a pi in the denominator. So what I basically end up doing is 1.5 times 180, which gives us 270 degrees. So it is a lot easier to convert from radians to degrees if those radians already contained pi. Okay. Next example, we have 175 degrees. So we're going to do 175 times pi over 180, which gives us 175 pi over 180. And again, we're going to divide by 5. And we're going to get 35 pi over 36 radians, which, if you want to think in terms of a decimal, is 3.054 radians. So now we have 3.75 radians, and we want to convert that to degrees. So unlike my last example where I had pi, I don't here. So I have 3.75 times 180 over pi. So if your radians doesn't already contain pi, our angle measure is going to be a decimal. So I could leave this as a fraction. I could do 3.75 times 180, and I could leave it as 675 over pi degrees. But that just doesn't really make sense. We don't really know how much that is. So what I'm going to go ahead and do is going to divide that 675 by pi, and it's going to give us 214.86 degrees. So I always want to round 2 decimal places at a minimum when I'm converting from radians to degrees, just to make sure I'm as accurate as possible. So let me know if you have any questions about intersecting chords or converting between degrees or radians or arcs in a circle.